over then instead is kind of how to solve this. I'm going to show you two different ways to do titration math right now. One is solution stoichiometry. One is kind of a shortcut that works under certain situations. So I'll start with question number 1 in this worksheet. We're going to do question number 1 and question number 7. The rest of it, whatever. I think the reading guide's going to cover some titration math. The Pogo packet will, so you'll get some practice with this anyways. Question number 1 on this problem says 50 milliliter sample of potassium hydroxide is titrated with a 0.8186 molar HCl solution. Titration requires 27.87 mils HCl to reach the equivalence point. What is the molarity of KOH? One of the main reasons why we do titrations is to solve for the concentration of something unknown. So you have an analyte, something that you're trying to analyze. You're trying to figure out what it is. Typically, that is going to be in your flask. The titrant is what you put in your burette. That's the thing that you add drip by drip wise, or a stream, in order to figure out that unknown. So in this question, you have a known molarity of HCl and a known volume of it. The KOH is what you want to figure out. Now, I understand that this worksheet doesn't have much space for stuff, so, off to the side if you want to, on a separate sheet of paper, whatever it might be. What I suggest, however, especially because I'm going to show you a shortcut, but the shortcut only works 50% of the time. I would always suggest writing out a balanced equation first. Remember, in a titration reaction, it's kind of like a double displacement reaction, where there's that switch. The K and the H are going to switch places. That gives us water, and that gives us an aqueous compound typically. KCl is definitely aqueous. Remember your solubility table. Anything that has an alkali metal, like potassium, sodium, always soluble in water. Now, to help out with my organization here, I'm just going to write down underneath here the values that were given to me in the problem. This was 27.87 milliliters. This was 50.00 milliliters. I want the molarity. Now, you could just easily just kind of highlight or circle those parts within the problem, but hopefully you're realizing by now the importance of kind of annotating a question in this class. You're given a lot of data. How do I use that data? In this question, we have a known concentration of HCl and known volume from the burette. We have an unknown concentration of KOH, but we have the volume that we started with. If we're asked to solve for that molarity, this is an example of solution stoichiometry, where if I start with my known thing, 0.8186, now molarity is the same as saying moles per liter. Are we okay with that statement there? I'm going to multiply that by my liters, 0.02787 liters. Because if I take molarity times liters, what does that give me? Molarity times liters equals moles. Remember back from Chem 1, we would do this little triangle. Molarity times liters equals moles. That's all I'm doing in this step number 1. Because if you have moles of HCl, I can then use the fact that there's 1 KOH for every 1 HCl, stoichiometry, to convert from moles of HCl to moles of KOH. And maybe I should have labeled this HCl to start with to make that a little bit more apparent. If I'm now in moles of KOH, to get to molarity, I have to divide by my liters of KOH. And if I do all of this, I would get this to equal 0.4563 molar KOH. Now, if you look at how I set up my stoichiometry and you're not having it, that's okay. Again, what we could do instead, so I'm going to try to show you as many different ways as I can, and you figure out which way works best for you. You could instead start by taking molarity times liters. That's what I did up here. 0.816 times the 0.02787. So you could do that as your step one. Then if you had blank moles of HCl, you still got to do the stoic. 1 KOH for every 1 HCl. Because that would get you to moles of KOH. Then from there, you could solve for molarity by doing moles divided by liters. So you could do it as 3 individual steps if you are not comfortable with setting it up this way. It's your choice of which one you prefer. Again, one of the things that we're going to start doing after we're done with all of our regular class stuff is practice tests. And what I usually do is I print off the answer keys that the College Board uses. And then if you look at a solution stoichiometry problem, like a titration problem, they're going to show it like this. That doesn't mean that's how you have to show your work, because the graders of this are AP chemistry teachers. They know there's more than one way to do this. So they can look at other versions and see, yeah, you still get what you're doing. Now, what makes this problem the simplest type of titration problem possible is 2 things. One, it's a strong acid, HCl, and a strong base, KOH. We cannot forget strength. We just turned in the lab what dealt with strength because the buffer had to be a weak acid in order for it to work. You're going to see that we are going to keep on going over strength for the next week still. It's a 1-to-1 ratio is the other reason why this is a simple problem. So the reason why I want to now skip down to question number 7 is it's not a 1-to-1 ratio. So I want to go over one more problem with you on this. And again, I apologize if 2 problems isn't enough. If we have time after everything else that I've planned up here, then yeah, let's feel free to look back at this and do some more practice problems. But I want to make sure we can get through titration curves today too. Yeah. Yes, and that's why number 7 is a dichloric acid. That's why I want to go over that. So number 7 says H2SO4 solution of unknown molarity is titrated with a 1.209 molar NaOH solution. The titration requires 42.27 mils of NaOH to reach the equivalence point with 25 mils of H2SO4. What is the molarity of the acid solution? Sulfuric acid is a diprotic acid, meaning that it has 2 hydrogens that have to be neutralized in this process. That's what makes this different. If I were to write out the balanced equation, if I have my Na and my hydrogen switch, I'm still going to make water. But now sodium sulfate is my other product. And because sodium sulfate's formula is Na2SO4, I need to put a 2 in front of my NaOH. And then to balance this, I'd end up having a 2 in front of my water as well. Again, for organization purposes, I'm going to write down then what I start with. I have an NaOH solution that's 1.209. And it took 42.27 mils. I have an H2SO4 solution where I want to find the molarity. Again, that's usually the point of a titration problem, is what is the molarity of the unknown. and I started with 25 mils. What makes this problem different than the previous is it takes 2 parts NaOH to react with the H2SO4 instead of a 1-to-1 ratio. And that's where your stoichiometry comes in. So I'm going to solve this the same way I first solved the previous problem. So I'm going to do kind of that stoichiometry method, where step 1 is I'm going to multiply molarity times liters of the NaOH. Because whenever you're in doubt of what to do mathematically in this class, get to moles. Moles is the unit in chemistry. So I'm going to take 1.209, again, moles per liter of the NaOH. I'm going to multiply that by the volume, 0.04227 liters. Again, hopefully you're aware that all I did to go from milliliters to liters was divide by 1,000. We need to be past that conversion. But notice how then liters cancels out, top and bottom. I have moles of NaOH. Now I can convert to moles of H2SO4. And there's 1 H2SO4 for every 2 NaOH. Now my NaOH cancels out. And I'm left with moles of H2SO4. If I want to get to molarity, molarity is moles divided by liters. So I'm going to divide by my 0.02500 liters. And this gets me 1.022. Okay, so this could be on the free response. This could be on the multiple choice. And that's where I want to go over a couple of things to hopefully help out if this were on the multiple choice. First off, technically, molarity is moles times liters. That's why I converted my milliliter volume into liters. However, if I were to have kept this in milliliters here, and I were to have kept this in milliliters here, it wouldn't have changed this value at the end. Are we okay with that statement? Technically, if I took molarity times milliliters, it would give me millimolar. Remember, beginning of the year, you did micromolar for the blue dye. But then if I then divided by milliliters at the end, it'd get me back to molarity. So you could save yourself, especially if you struggle with metric, which, come on, man, it's just dividing by 1,000. But if that's a mistake that you make, if I always write it as 0.4227, I'm always off by a power of 10. Well, we could avoid that. If you're given the volume for both in milliliters, technically it's not the correct way to do it, although units cancel out, and you would get the same answer there anyway. So that might be one thing to help you out along the way, is you might not have to do metric. By the way, if this was given to you more on the multiple choice, where you had to do math in your head, it wouldn't give you 42.27. Again, the math they give you is nice round numbers. So they try to make things work out for you. The second thing I want to bring up. Now, this is the one I'm a little hesitant to bring up, because once I show this to you, you want to do it all the time. The second thing I want to bring up to you. If we look back at this first problem, in order to get this and this to neutralize, because it's a strong acid and it's a strong base, its equivalence point is going to be at a pH of 7. Doesn't that mean the moles of the acid has to equal the moles of the base? Do we like that statement? Since this is a 1-to-1 ratio, in order to get them to balance each other out. Moles of acid equal moles of base. If that were the case, where the moles of acid should equal the moles of the base at the equivalence point, how do I solve for moles? What times what? Molarity times liters, right? So molarity times the liters, which could be a volume because it doesn't have to be in liters. We talked about that already. Does this look familiar? We use this equation for dilution. Because when you dilute something, you're just adding water. It's the same number of moles start to finish. It's just in a different volume when I dilute it. Well, in this case, if I took molarity times liters of my acid equals molarity times liters of my base, it's going to give me the same thing. So if I go back to this previous problem, I could just as easily plug this in here, where my acid had a molarity of 0.8186. The volume that it was in, heck, I don't even care if it's in milliliters versus liters, 27.87. M2 I can call it. I don't know. My V2 I do know, 50 milliliters. Because what do I end up doing? I end up multiplying these two numbers and dividing by 50. What did I do up here? I multiplied these two numbers and divided by 50. This only works if it's a 1-to-1 ratio. If it was a 2-to-1 ratio, you could do M1 V equals M2 V2 and then put a 2 involved in at the end, yeah. So there is a way to still make it work if it is a 2-to-1 ratio. Typically in the past, I've seen students not know should they multiply by 2 or divide by 2, so I tell them if it's not a 1-to-1 ratio, I would go back to solution stoichiometry, because this is kind of a shortcut way to get it done. But it's also understood that it's a shortcut way that works when it's a 1-to-1 ratio. So the surefire way is solution stoichiometry unless you like to take it in a 3-step process like I outlined here. However, if it is a 1-to-1 ratio, you can do the dilution equation more or less to solve for that. And that will give you the same type of answer.